So how many
Yes,
classes you have attended till now? How many subjects?
ma'am, yesterday PPS ର ଗୋଟେ class ହେଇଥିଲା
And
and ma'am
today?
ଆଜି ଗୋଟେ lab class ହେଲା ଆଉ chemistry class ହେଇଛି ma'am 10:30 ରୁ।
And our next class will be on Thursday, right?
Yes.
This is for the online classes. I will detect your attendance. I mean, I will take your roll call. Okay. Except that I will download the Google Meet attendance, and I need one of your student. I mean, Pratiswata is your GR, and who is your CR? Pratiswata, who is the CR?
I'm Rudra.
Rudra.
Rudra, man, me.
Rudra Narayan. Okay. Both of you
Yes,
have
ma'am.
to take the screenshot. At the end, after the roll call,
Okay, ma'am.
I will instruct you to turn on your camera for 2 seconds. All the students will turn on their camera, and you have to take a screenshot. Okay? Is it clear
Yes,
with
ma'am.
Pratiswata and Rudra?
Yes, ma'am.
Okay, very good. Is it visible? My screen is visible to you?
Yes, ma'am.
Yes. So we have already covered the part what is p-type and n-type. Then we have jumped to what is p-n junction, right? And we have discussed how the p-n junction is being formed. Okay. So now what we have discussed in the earlier classes are in the p-n junction diode. What happens when we combine a p-type material and n-type material? We merge them, then what happens is in n-type material, the majority charge carriers are electrons, right? You have to communicate with me. Okay, all of you have, you can unmute yourself at any time and you have to communicate. Okay. So now in the n-type material, what is the majority charge carriers?
Electrons.
Free electrons.
Right. In the p-type material,
Holes.
Holes.
holes, right?
Whole.
So when we merge the p-type and n-type, what happens is the majority charge carriers from your n-type material, that is the electron, and from the p-type material, that is the holes, they will diffuse
Diffuse.
Diffuse.
into the other part of the region, right? From the N to P and from P type to N type, right? So that is the diffusion process, you know. But after diffusion, what happens is the remaining uncovered ions, right? They will gather at the junction, isn't it? Near the junction, the uncovered ions will gather because the donor atoms will have one free electron, whereas the acceptor atoms will have holes, right? Isn't it?
Yes.
Yes.
Right. So after the free electrons and holes they diffuse, what remains is the immobile charge carriers, or you can say the ions, right? Uncovered ions. Then they will gather at the junction, isn't it? So they will form one depletion layer. Correct?
Yes, ma'am.
Yes,
Right.
ma'am.
So why the
Yes, ma'am.
name is depletion layer? Why the name is depletion layer? Who will answer?
Because it carries free electrons.
Is that so? Depletion layer carries free electrons.
No,
Get
ma'am.
that answer.
Because
What is your name?
No.
because the mobile charge carriers are depleted from this region.
Very good. What's your name?
Nikita Priyadarshini, ma'am.
Nikita Priyadarsini. That is where that answer is correct. Very good. This name is depletion layer because the mobile charge carriers have been depleted from that region. Why? Because you can already see that the electrons from the n-type material, here the majority charge carriers are electrons, right? They will diffuse towards the p-type region and the holes will diffuse to n region, isn't it? After that, these immobile charge carriers, or you can say the uncovered ions, will gather at this region to form the depletion region. So in this depletion region, no electrons and holes are there, no mobile charge carriers are there, only the uncovered ions are there, right? That's why the name is depletion region, because the mobile charge carriers have been depleted from that region, right? So what about the outside? What about outside of this region? What happens outside the depletion layer?
One electric field is appeared.
Electric field is appeared where? In this depletion layer itself, right? That is your barrier potential, isn't it?
Yes, ma'am.
Right. The barrier is created by these ions only, and that will provide an electric field. That is your barrier potential, right? It is denoted as V naught here. But outside this depletion layer, the material is always neutral. Okay, always remember that. Outside the barrier, each side of the junction, the material is still neutral. Okay, I guess I have told this part. Still,
Yes,
I
sir.
am just
Yes, ma'am.
revising it. Outside this barrier, each side of the junction, the material is still neutral. Only inside this barrier, or you can say this barrier only provides your barrier potential, that is your V naught, right? So now we will go for the biasing. What is biasing? You can write down the term biasing refers to the application of external, write down the term biasing refers to the application of external voltage across the two terminals of the device. As you know, our diode is a two-terminal device, isn't it? The symbol of diode looks like this. Correct? Correct or not?
Yes, ma'am.
This is the P terminal. This is the N terminal. If you remember, I have already told you the triangular part for the P type is derived from the P alphabet itself, right? And for the N terminal, it always derives from this alphabet N. So this bar is from the N alphabet, and this triangle is coming from the P alphabet. So always remember, this triangular terminal denotes the P terminal or the positive terminal, and the bar terminal always denotes the N terminal. Okay. So what about forward biasing and reverse biasing condition? First of all, what is biasing? Biasing means applying some external voltage across the terminals to extract a response. It means you will apply some external voltage across the terminals to see what happens to this device when the polarity given by the external potential or by the external voltage source, how it will influence the flow of electrons inside the device, right? That is your biasing. If I apply some external voltage or external potential, what happens to the flow of electrons inside the device, that will be seen by the process biasing. Okay, you can write down the term biasing. Note it down. All of you, please note it down. The term biasing refers. All of you, note it down. The term biasing. The term biasing refers to the application of external voltage. Am I audible to you?
Yes,
Yes,
ma'am.
ma'am.
Okay. The term biasing refers to the application of external voltage across the two terminals of the device to extract a response. Okay. So that is why we will study about biasing for this PN junction diode. Okay. So biasing always gives rises to three conditions. Okay. First of all is, you can say first is your no biasing state. We will go for no biasing state. Then we will study about, first we will go for no biasing state. Then we will go for forward biasing condition. Then reverse. Listen, my handwriting, you can see it is not that good for this online domain. Okay, because I'm using my mouse to write down these letters or these words. Okay, so if you are having any doubt for these words what I am writing, or you can't understand my alphabet, then you can ask anytime. Okay, am I clear?
Yes, ma'am.
Yes, ma'am.
Okay, because I'm using my mouse to write down the sentences or words in between. Okay, these are predefined, but whatever I'm writing on the platform live, those are little bit here and there, so you can always ask me. Okay. So we will study about no biasing, forward bias and reverse bias condition. Okay, these three conditions we will see. That is called as your diode operating condition or diode biasing condition. Diode operating conditions you can call them, or you can always address them as biasing conditions. So first of all, we will see no bias state. We have already discussed about no bias test. What happens when the diode is at no bias? No bias means no external field is being applied. Only diode is just kept like that. So what happens? The diffusion will occur, right? Isn't it? जब मैं खाली P type और N type को merge करेगा. No biasing state means we are not applying any external field, or we are not giving any potential to that diode or to that device, only keeping the device as it is at normal condition. So what will happen? Of course, P type and N type are coming together means diffusion will occur, isn't it? Electron flow from the N type to the P type, and the holes from P to N movement will occur, and the diffusion process will take place. For that diffusion process, this depletion region will also be created. Yes or no?
Yes, ma'am.
Yes.
Yes, but as we are not applying any external voltage or any external potential, we are not applying to the device, you can see still the device will remain at neutral condition, isn't it?
Yes, ma'am.
Yes, right. So no current will no current flow will be there, because only the depletion region is being created. Diffusion is there, so no current flow will be there. Yes or no?
No, ma'am.
Right. So if we see the diode, this is the diode symbol, you know, right? So P type, N type, you know that part, right? So ID will be 0 milliampere because in no biasing condition, no current flow is there. Okay. So if you go for the two terminal device, always remember that in no bias state, in no biasing condition or no bias state, the diode, the two terminal device, the diode has no current flow, okay, through the device. Okay, now we will go for forward biasing and reverse biasing condition. Okay, why forward biasing and reverse biasing condition? Because there are two terminal, that is two terminal device, so we will provide each terminal two different polarity. Once we will provide positive polarity, again for the same terminal we will provide negative polarity. Okay, according to that we are considering two biasing states, one is forward and one is reverse, because we are having two terminal device. For each terminal we will provide two polarity, one for positive polarity and again we will give the same terminal negative polarity. So first of all, first condition is forward biasing. In the forward biasing state, as we know, this is the PN junction diode. So this is P type and this is N type material. So for that PN junction diode, the P terminal you will connect to the positive potential, and if you connect the N terminal to the negative potential, then you will find it forward biasing state. Okay, to make the diode or to keep the diode in forward biasing state, you have to connect the P terminal of the PN junction diode to the positive terminal and the N terminal of the PN junction diode to the negative terminal of an external battery. Okay, or external voltage source. Okay, biasing means we are providing an external voltage source, right? Suppose I am writing this is E1. Okay, for the battery E1, the positive terminal of the battery will be connected to the P terminal of the device and negative terminal of the battery will connect to the N terminal of the diode. Correct? This much correct? बुझी पालो समझते? Or
Yes,
having
ma'am.
any doubt?
Okay, ma'am.
So,
Yes, ma'am.
okay. So for forward biasing, what is forward biasing? You can say when external DC voltage is applied to the junction in such a direction that it cancels the potential barrier, thus permitting current flow, it is called forward biasing. Okay, this statement we will understand first. Okay, for this statement we will analyze what happens in the forward biasing condition. We have connected the positive terminal here and we have connected the negative terminal here, right? So what is the majority charge carrier in N-type material? You know that is electron, and majority charge carriers in the P-type material is hole, right? So holes are the majority charge carriers. Here electrons are the majority charge carriers. As we are giving negative potential here and positive potential here, so the same potential will repel, isn't it? So as we are providing negative potential here, means they will force the free charge carriers in the N-type material, that is electron, to move towards the junction. Correct or not? And holes here positive, and holes are also positively charged. They will repel and they will force, this positive potential will force the holes here to move towards the junction. Correct or not?
Yes, ma'am.
ଆଉ କାହାର ଡାଉଟ୍ ଅଛି? ବୁଝିପାରୁଛ ନା ବୁଝିପାରୁନ? When I am applying the application of forward bias potential, or when I am applying forward biasing to the diode, means I am applying positive potential to the P terminal and negative potential to the N terminal, right? So as the electrons are the majority charge carriers in the N-type material, the negative potential will force these electrons to move towards the junction. Similarly, this positive potential will force the holes to move towards the junction. isn't it? Now what will happen? Electrons are moving in this direction. P-type material, holes are moving in this direction. So what will happen? As we know here, in no bias condition, first you will keep the diode in no bias condition. No bias condition re kon hoji? Already gote varied potential is there, isn't it? Depletion region is there. Yes or no?
Yes, yes, ma'am.
Right. So the uncovered. Yes, anyone is saying something or what? Any doubt? If you are having any doubt, you can ask anytime. Okay. So if I say already in the no biasing condition, the uncovered ions are here, isn't it? If I refer to the previous, you can see this depletion region is already there, isn't it? In no biasing condition. So now what happens is already the depletion layer is there, and again we are forcing the electrons to move in this direction and holes to move in this direction. So what will happen? They will create a pressure on these electrons and on these holes to recombine with the ions near this boundary, isn't it?
Yes, ma'am.
Already in this depletion layer, it is having the uncovered ions, right? So it will again force these electrons and holes to move in the same direction. So what will happen? They will recombine with this uncovered ions, right? So when the recombination occurs, what will happen? The depletion region, the width of the depletion region will reduce. The width of the depletion region will reduce. Yes or no?
Yes, ma'am.
Because recombination again occurring, right? So the uncovered ion count will reduce, hence the depletion region width will automatically reduce, isn't it? So basically what happens in forward bias condition is you are applying an external potential or an external DC voltage to the device that will force the electrons from N-type and holes from the P-type to move towards this junction, which will recombine with the ions which are already present in this depletion region, and they will reduce the width of the depletion region, right? So you can write down, that's why this definition is here. When external DC voltage applied to the junction is in such a direction that it cancels the potential barrier, thus permitting the current flow, it is called forward biasing. Because of this depletion region of width coming along, right? So the resistance, the depletion region provides some resistance, isn't it? That will reduce. Yes, ma'am. Now this electron can easily move from this to this direction, and the holes can easily move from P to N-type, isn't it? Already negative potential achi, 80 positive potential achi. So this positive potential again attract these electrons. Yes or no? This positive potential will attract